Hello, welcome back. In section 7.6, we're solving trig equations. There are two types of trig equations that we're going to be looking at, two basic types. The one type is linear and one type is quadratic. And if you can't, I'm telling you what they are now, but if you aren't sure, what I always recommend you do is take each trig function that you see in the equation and assign it a different variable. So, for example, all I see is a sine theta in this first equation. So if I rewrote that and chose some variable to represent the sine of theta, we could use x, but a lot of times you might see your variable with the trig expression be an x. For example, that could be 4 sine x minus 2 equals 4, which is the reason why I typically don't use x. But a popular substitution we do in math, and you will do it in calculus, is what we call a u substitution. So if I I'm going to let sine theta be u. So I'm going to say u is sine theta, and then I'm going to rewrite the equation in terms of u. So instead of a sine theta, I have a u. So 4 times u minus 2 is negative 4. So now you can see it's more algebraic, right? And how would you solve this equation? You would isolate u, right? It's a linear equation, so you want to get it solved for u. U is what? Okay, same strategy that we use with this trig equation is we're going to isolate the trig function and then figure out what that unknown variable is, theta. What is theta? What is that angle that when I put it into that equation, it makes a true statement? Okay, so over here, I can see that this is quadratic because my trig function is my highest power is squared, so we say it's degree 2. So if I think of a substitution, if I let u be cosine theta, then everywhere I see a cosine theta, I'm going to put a u. So I could rewrite this equation as 2u squared plus u minus 1 equals 0. And then it looks like a regular old algebraic quadratic equation, which then we solve using methods for solving quadratic equations, which typically first we try to factor. If factoring doesn't work, we can use quadratic formula. There are special situations where square root property might work if we only have a squared term. Or there was another method that some people chose, but most people do not, and that would be completing the square. I typically never use that with trig equations, but there are sometimes in algebra where completing the square is actually faster and easier than quadratic formula, but that's a whole other class. All right, so let's start very basic. Oh, but before we do, it would be very helpful if you would follow this procedure. It'll save you in situations where you're tempted to do something that's wrong. Okay, first thing, is it linear or is it quadratic? And then you can decide what are the methods that we use for solving those types. Okay, if there is only one trig function present, then we want to solve for that function. So we would try to get that trig function isolated. If more than one trig function is present, then you want to rewrite it so that one side equals 0. So you want to put everything on one side equal to 0, try to factor, and then apply the zero product property. If it is clearly quadratic, then once again, or quadratic in form, you would set it equal to 0 and try to factor. If it's not factorable, then you could use quadratic formula. And then, of course, we could always try identities to rewrite it into something that we do have a method for. Okay, so let's start out with some basic linear equations. We've actually looked at this situation, but we were a little more restricted back in chapter 5 when we first saw these. But our goal, just as with a linear equation in algebra, is to isolate the variable on one side. So here, it's similar that we're isolating our trig function, not necessarily our variable, but our trig function involves a variable. Then we can figure out what that variable is based on what we know about that trig function value. All right, so for example, the sine of x equals negative square root of 2 over 2. Okay, so I'm trying to figure out x. What is x? Well, x is an angle in degrees or radians. We'll have to know which one we want. Whose sine is negative square root of 2 over 2. Okay, so think back to what we know about the sine of an angle and the fact that I recognize that negative square root of 2 over 2 is a unit circle value. So angles on the unit circle that have a sine value that is negative would terminate in quadrant 3 or quadrant 4. So we're looking for an angle in quadrant 3 or 4 whose sine is negative square root of 2 over 2. Well, I know that's a 45-degree angle multiple or pi over 4 multiple in quadrant 3 or 4. So let's mark those. How about with a star? All right, so these are my angles. Okay, that's or I should say the point on the terminals, or the point on the unit circle associated with that angle. All right, so I know in quadrant 3 that x is so we could say then that x is 225 degrees in quadrant 3, or if we were doing radians, that would be 5 pi over 4, or in quadrant 4, that's going to be 315 degrees, or 7 pi over 4. Okay, now, are those the only two angles that have a sine of negative square root of 2 over 2? No. Those are only the two angles between, these are solutions on the unit circle. So that means they're solutions in the interval from 0 to 360 in degrees, or 0 to 2 pi in radians. So notice how I'm putting a parenthesis on the 360 and the 2 pi because 0 and 360 are coterminal, so we don't want to list them twice. Okay, so if we're only giving solutions on what I call one trip around the unit circle, then we restrict it to in a certain interval. Okay, if we want to give all solutions, because we know there are infinitely many solutions, we know there are infinitely many angles that have that value. So if we want to give all solutions, then we have to come up with an expression that will calculate x and give us all angles. So we've used that expression. We've used that idea by using integer multiples. So if I start in degrees, I say, okay, well, it's an angle of 225 degrees or any angle coterminal. That means we need to add and subtract multiples of 360. But if we say integer multiples of 360, then that does the adding and subtracting for us. So we've used that N notation back when we were in chapter 6. All right, so the other one would be then that x is 315 degrees or any angle coterminal, so we add integer multiples of 360 as well. So these would be the expressions that would calculate every single solution. Okay, if we wanted radians, then we would just simply use two integer multiples of 2 pi. So just have to be careful of which we want. All solutions or all solutions in a certain interval. Then, of course, you could choose an angle, go back and substitute it in for x and check. All right, so how about this one? Tangent of theta is 0. So theta is an angle that when I take the tangent of that angle, I get 0. All right, so let's do this one in degrees. And so if you think about this, then we know that the tangent of an angle is the sine of the angle over the cosine of the angle. So if I end up with 0, 0 is 0 over 1, okay, if we're thinking unit circle. So that means I'm looking for an angle on the unit circle whose sine is 0 and cosine is 1, or it could be, oops, no, I messed up. Okay, try this again. Or it could be over -1 as well. So where on the unit circle is the value of sine 0? Okay, well, sine is 0 at 0, or 360, or 180, or any angle coterminal. Okay, so if we're going to give solutions in degrees between 0 and 360, it's basically one trip around the unit circle. And as I said earlier, this could be 0 over -1, which would come out to be 0. All right, so we could say that theta is 0 degrees or 180. Okay, now if you're tempted, remember 0 is coterminal with 360. So if I say 360 as well, then yes, 360 is a solution, but here this means that 0 is included in the solution set. The parenthesis means 360 is not, just because those are coterminal. So my solution set would technically be the angle 0 degrees and the angle 180. All right, so if we're going to give all solutions, okay, I want an expression that will calculate every single angle coterminal. Well, if I notice that these two angles are equally spaced, to get from 0 to 180, I add 180. To get from 180 to 360, I add 180. Okay, so I could say, oh, it's 0 degrees plus 360n, or I could say theta is 180 degrees plus 360n, but that's very redundant, okay? or we could be more concise, I should say. So I could combine this into one statement because they are evenly spaced 180 degrees apart. Whereas my last example, they were not evenly spaced about the unit circle. So here I could say 0 degrees plus 180 n, because if I keep adding 180, I get to an angle. Or we could even make it more basic and just say 180 n, because if n is 0, then I get 0 degrees. So all are acceptable, but it's probably better to get one expression that calculates it versus two of them as we had originally. Okay. Ooh, this one looks fun. All right, a little more work. All right, first of all, I can see my equation has one trig function, secant theta, to the first power. So this is a linear equation. So what are we going to do? We're going to isolate that one trig function on one side. Okay, so I'm going to get secant theta all by itself. So I'm going to first subtract 2 square roots of 3, and then I'm going to divide by 3. All right, now when I look at that, I'm thinking, square root of 3s and 2s. I'm thinking this could be a unit circle value for secant, but I'm not as comfortable with all my trig function values as I'm not as comfortable with trig function values other than sine, cosine, and tangent, because I do those the most. So I'm going to rewrite this as cosine. So if we know the secant of the angle, we know the cosine is the reciprocal. So the reciprocal would be negative 3 over 2 square roots of 3. All right, well, if I rationalize that, try and pretty it up and see if I can get it to where I do know that it's a special value. Let's see what happens if we rationalize. So I end up with, go this way. I end up with negative 3 square roots of 3 over 2 times 3, which is 6. Which then is going to reduce down, because 3 and 6 have a common factor of 3, is going to reduce to negative square root of 3 over 2. Oh, I know that one. All right, so this is what we're looking at. All right, I'm trying to figure out what's an angle whose cosine is negative square root of 3 over 2. All right, so what quadrant is cosine negative in, or which quadrants is cosine negative in? Cosine is negative in quadrants 2 and quadrant 3. So I'm looking for angles in quadrants 2 and 3 whose cosine is negative square root of 3 over 2. Well, cosine of square root of 3 over 2, that's going to be in degrees, 30-degree multiple, or an angle whose reference angle is 30 degrees. So that would be in quadrant 2, reference angle. Oh, whoops, I don't like that one. That one doesn't show up very good. Let's go back to our smiley faces. Here we go. Would be this angle and this angle. Okay, so reference angle of 30 degrees in quadrant 2. Theta is going to be, so we could say then that theta is 150 degrees. That's quadrant 2. Quadrant 3 would be 210 degrees. So if I wanted to give all solutions, then I would say theta is 150 degrees or every angle coterminal, so plus 360n. Notice how these two solutions are not evenly spaced. The distance between them is different. For example, that's what, 60 degrees? If I want to get from here to here at 60, I would have to go a whole, 300 to get to there. So I have to write two separate expressions. So theta then would be also 210 degrees plus every angle coterminal. All right, one more example. All right, now we're going to find all solutions between 0 and 2 pi, which is telling me when this is in radians, I will give my angles in radians. Okay, all right. Now let's look at this equation. First of all, I see only one trig function, cosecant, and notice how it is to the second power. So technically it is quadratic. Okay, and two things here. It's quadratic, and there's only one trig function. So I could set it equal to 0 and see if possibly I could factor, but this is very similar to an algebraic equation. Not sure why that happened. Well, I am sure. Okay, similar to algebraic, if I said cosecant is u, it would be u squared plus 2 equals -1. So this looks like the perfect situation to use the square root property or isolate that u squared. Okay, so same thing here. I'm going to isolate the cosecant squared by subtracting 2. So I get cosecant squared of x is -3. Okay. Then if we were going to get rid of the square, we would apply the square root property. Remember, this means take the cosecant of that angle x, square it, and get -3. So if I apply the square root property, then I say the cosecant of the angle is the plus or minus square root of -3. Well, there's a problem. Square root of a negative, okay, this is not a real number, which means there is no solution to this equation. There's no solution, or we could say we can use this, which means the empty set. Or another way of writing the empty set, remember, is to do the braces with nothing in the middle. Okay, now if you caught that back here, that's awesome. We're saying we're taking something and squaring it and getting a negative. Remember, no matter what we square, we always end up with a positive. So there is no angle that when you take its cosecant, square it, add 2, you get -1. And that's it for our intro to 7-6 solving linear equations. We'll be back with more types of equations in the next videos. Stay tuned.